Okay. Um, TERA6G is a project that in summary is bringing terahertz technology in communications, especially aiming for 6G. Today, Angel Alexiou was aiming to be here with me, and you will see why we initially thought about having two presenters. Uh, our project is composed of 10 partners in the consortium, and this basically combines partners from photonics technology and network management, as well as key industry like Cumucor, Intracom, and Telefonica. Telefonica is a major carrier in service provider in communications, and we are using them mainly to guide our research. This consortium also builds upon several projects, H2020 projects, TeraWay providing or developing photonic integrated hardware for wireless communications, and then Ariad, Terranova, and Fudge 5G, which are aiming to in beamforming and multi-MIMO systems. And all this experience is combined together in our network. So basically, we have photonic integrated for wireless communications partners like ICCS in Greece, Fraunhofer HHI in Germany, Lyonix International in the Netherlands, and FIX. This is our major assembly and packaging partner. And then we have University of Piraeus, Oulu University, and Cumucor Intracom that are mainly strong in network development. So this combination allows us to focus on one thing that you can remember this project by is enabling fiber over the air. Basically, we want to achieve this terabit per second capacity on wireless links. And we are pushing this to provide agility. Basically, we want to provide wide channel bandwidth up to 30 terahertz and continuous frequency tuning. That means the carrier frequency can be shifted continuously from 30 gigahertz to 450 gigahertz. And these are the advantages that we have when we use photonics technology to address these high frequencies. Then we are aiming for scalability. That means that our chips are going to be integrated multiple beams. This is basically one device will be able to provide multiple beams for communication, independent beams. As in this microsite, we aim to use this to provide one device generating the different beams, connecting different sites. And we are going to be able to reconfigure these beams to be able to switch them on and off. This is for energy savings. We will dimension the capacity for the demands of the users. And we are also going to be able to reconfigure the functionality so these beams can be used for communications, for channel sounding, or radio ranging. Basically, what we are aiming to use is the photonic integrated circuit, wide frequency bandwidth, and the scalability of the system to provide this reconfigurability. This is how this is connected. And now, quickly speaking, how we are going to do this, because I just mentioned we are going to use photonic integration technology. We are going to enable this fiber over the air concept through photonic integrated circuits. So the objectives of the project is basically, in terms of the hardware, is to develop these chips. Actually, these are combined, the combination of different material platforms that we call these chiplets. And each chiplet is responsible for N beams. This means that a pair of lasers will generate single carrier frequency, but this at this carrier frequency, we can have different beams going into different directions. And this is going to be provided by an optical beam forming network in the optical domain, which avoids power penalty in the generation of the steering of the beams. And this frequency, these laser wavelengths are going to be mixed in these photodiodes with indium phosphide, with silicon antennas, basically to be able to radiate efficiently the millimeter waves and terahertz into air, and in an array form factor. And of course, this is one of the key challenges that we have because of the complexity of routing so many signals. And we do this aided by a polymer platform that allows us to do 3D interconnection paths. And once we have this, the idea is that and to scale up the capacity of our transmitters, that's why we are developing these chiplets, because repeating the same idea, we are able to add different carrier frequencies and increase the capacity. And all of this, the goal is to do this on a photonic integrated circuit form factor. In the transmitter, we are using this is a blast matrix in optical beamforming network. In the receiver, we are aiming to do the same. In this case, the beams, we are receiving the signals, and basically what we have here is these lasers to generate the LOs. And now we only need to shift the phase of the same wavelength, basically to steer the beam and in the different receivers. So we have a different technique to achieve the steering of the receiver beams. But basically, it's the same structure that we can scale up on the chip. And photonics, it's one of the advantages that it's changing the frequency of the lasers. We can achieve a different carrier frequency just by tuning. These are continuously tunable laser diodes. And thing is that these are electrically tunable. That means that we can shift the frequency, and that is what allows us to propose that this can be used to generate a fixed carrier, or in the other another use is to shift the frequency to have a FMCW radar, and that's the sensing that we aim to add. Of course, adding this scalable capacity and functionality needs that we also add the control of these devices by the network, and that's the other part, the other partnership, the other know-how of the partnership in this project is partners that have developed algorithms to scan and aim connect the beams to the user, and of course also use this to make energy efficient transmitters that can switch on and off these beams as they are needed and directed to the right place where the user is expecting to get this functionality. And since we have such a broad bandwidth, we can define different channels that can be part of the slicing of the network. And it doesn't matter which modulator or which laser is providing the functionality, because actually what we are providing is a broad bandwidth that will be managed by the electronic control. And with this, I just want to finish with some of the figures. This project will be running for 42 months until June 2026. The overall budget is a bit over 6 million, with a EC contribution of around 6 million. I'm the project coordinator. You can actually reach information and all the links to the social media where we have Instagram and LinkedIn links to find more information. It will be, all the news will be posted in our project website, And right now you can find it you can find me in LinkedIn, and you will already find some information about the project. And with this, I think I'm done.